So let us look at some problems related to equilibrium of concurrent forces. So the question here is described: the following coplanar forces pull on a ring 200 at 200 Newton at 30 degrees, 500 Newton at 80 degrees, and 300 Newton at 240 degrees at unknown forces. Find them. It asked us to find the magnitude of the unknown force if the ring is to be in equilibrium. So let us think of a resultant vector. Something is in here. So let us think of a resultant vector and it's denoted as R, right? It's the R1. Now there are three vectors at three directions, and there are several forces, and they're indifferent of each of them, and the angles are also not the same. If we are assuming a resultant here, so the resultant we are assuming is the integration of those rest of the forces and their vectors. So Rx, we can easily tell that R equals Rx plus Ry to the power half. That's the main thing we're gonna tell. That is the thing. So now right here, what is the Rx then? Right, the Rx, the value of the Rx, it should be the integration of the forces, the rest of the forces at x direction, at x axis. So in respect of x axis, the forces in respect of x axis, we have to get that here. So if we write down that, if we assume it is the 200 Newton, the magnitude is modulus of F1, the 500 Newton is modulus of F2, and the 300 Newton is modulus of F3. If we assume it, then we should write that F1 cosine theta 1 plus F2 cosine theta 2 plus F3 cosine theta, right? It should be the formula of x. Similarly, if we copy and paste it, and if we write that if we replace this x with y and the cosine with sine, then there's it stands out the formula of the forces, the resultant forces of the rest of the vector forces in respect of y-axis, right? So the the collective the collective force is represented as r. If we assume, so this r isn't r only, it's f, and this is fx, this is fy. So if we calculate fx equals, then it's 200 Newton cosine 30 plus there's f2, right? There's f2, which is 500, and now it's not 30, it's 80. So you have to write cosine 80 and then plus, and then now for the third cos, it's 300 Newton the magnitude, but the angle is in 60. The angle is 30 plus 80 plus 180, 30 plus 80, we shouldn't be bothered with it. 180 is the thing. See, that okay, I'm sorry. Okay, that this right here, it's 180, it's 180 degrees, right? It's right here, it is 180 degrees. So if it's 180 degree and there is 60 degree in addition, so it should be called 240 degrees in total. So the 300 Newton is 240 degrees in respect of the x-axis. 300 cosine 240. Okay, if we have gotten the force in respect of x-axis, we will also get the force in respect of y-axis, the integration of the rest of the forces at y. So if we type, just replace the x with y and the cosine with sine, and the formula is derived. So this is equals something of, if we calculate 200 cosine 30 plus 500 cosine 500 cosine 80 plus 300 cosine 240, then it is 110.029 something. 110.029 Newton. And if we calculate this, so it should be 200 sine 30 plus 500 sine 80 plus 300 sine 240. So it's 332.59, we can assume 332.6. okay, 332.6 Newton, right? So the force, actually the final force, and the force we were asked in the question actually was the integration or the collective force the collective force of the rest of the vector forces in respect of x-axis and in the respect of y-axis, both collectively. So root over, or if we can say one, okay, I think there's a mistake. It's not only rx, it's rx square, then it's, yeah, so it's rx square plus ry square and whole to the power root over, or whole to the power half. So the f here, it should be the 110.029 whole square plus 332.6 whole square, and then there's another whole because it's covered with bracket, it's closed with bracket, and there's half to the power half. So it's equal then let me calculate in this calculator. Okay, so it's 350.3 if it's not wrong, it's 350.32. so 350.32 Newton. Okay, the answer should be 350.32 Newton. So there is another problem. So it said that the value of W is 180 Newton. Here W is denoted as weight of an object, right? It's the weight of an object. So the value, the magnitude of the weight is 180 Newton. Find the tensions in ropes A and B. Let us try that sum. So it asked us to find the tensions in ropes A and B, right? So let us draw a free diagram of it. Okay, so if we draw kind of something like this, the x, it's the force, right? The free diagram. So this is what's happening actually. The weight, the gravitation is working downwards. Obviously it works downwards. The object is trying to get to the ground with mg, so it's W. And then there are two forces. Let us assume this is T1, two tension forces. This is T1, another one is T2. Now if there's T1 and there's T2 and there's mg, right? It asked us to find the value of T1. So basically what we can do is we can just think of something, think of a solution which is very creative, not if we think it the other way rather than thinking it very straight, so it will create some problems. So it can be the 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 way I'm looking at this sum is it can be solved by the Lami's law, uh, but we can also solve it in a different form, which is via drawing free diagram. So here, if we consider it as 53, so it is something which it is something the force and the component of this is working at cosine 53 degrees. So this should work as it, and we can also use the Lami's law. Instead of drawing a free diagram, we can use a Lami's law actually. The Lami's law is actually, using the Lami's law, the sum will be so easier than before. So the W is by the sine of 180 minus 53, then it's equal to the tension along this x-axis, T1, the A, the tension 1, and it's angled with 90, if I'm not wrong, it's 90 plus 53, so it's T1 by 90 sine 90 plus 53. So that is the main formula. No, that's not the structural formula, actually it's the derived formula. So here the W, we know the value of W, which is 180 Newton. Let us type 180 sine, and then okay, just copy the rest of the part. Oh, sorry, didn't copy it. Okay, now it will copy. Now it will paste as well. Okay, so 180 sine 180 by sine 180 minus 53 equals T1 by sine 90 plus 53. We don't know the T1, so we have to get the T1, so we can calculate the T1 from here. We can easily calculate the T1 from here actually. The T1 should be, okay, if I calculate it in my calculator, where's my calculator? Okay, there's my calculator. So 180 sine 180 minus 53 sine 135.64 135.64. So we got the T1. Now we want to have the T2 as well. So the T2, to get the T2 is the similar approach we have to take. It is that according to Lami's law, this part, the left hand side part will remain the same, but now it's 42, so the right hand side will get changed. So T2 42, it's by sine divided by sine of 90 degrees, right? Sine 90 degrees, right? So sine 90 is basically sine 90 is equals 1. So this, if we can easily say that the w divided by sine 180 minus 53 equals T2 is straight. So 180 divided by sine of 180 minus 53 is 225.38. 225.38 Newton, right? So okay, not this, 225. 225.38 Newton. So it's our T2, right? It's the answer. The T1, we got the answer of T1. It's 135.64 and the T2 is 225.38. Let us look at this problem. So there is an object tied up with two ropes hanging and with along the support of two ropes, and they are hanging with the support of two ropes which are clamped with ceiling and wall respectively. And it's there are tension forces in against of that weight, and there are more tension forces following the pattern. So the question asked us the figure, this is the figure, and the question asked us to find the tensions in the ropes. So there should be 3 steps that should be implemented to do or solve this kind of sum. So if we just think very normally, just forget about all other things, we have to think individually and very distinctively. So that's how we can get our things very pivotal at once. So if we follow our steps, so this is okay, if we follow our steps, these are the 3 steps by following which we will be solving this problem. So the first step is to think about the W, T1 and T2. This W, T1 and T2, we have to think about it separately. So what about it? So let us draw a free body diagram. This is x-axis, this is y-axis, right? And yeah, so this is x-axis this is y-axis, the perpendicular of x-axis, and then there is a object. Now this, on this axis downwards, for the force, for the object, the weight 600 Newton is working downwards for the gravitation. And the x-axis, on the x-axis, if we think about the ropes, if we draw the ropes, actually separate, if we draw this rope, so okay, so if just think of this two ropes, so if we draw this and there's also another tension right over here. This is T1, this is T2 walking, this is, and this is our mg working. Okay, let me just fix this real quick. Okay, we can't. Okay, this is our mg at downwards working, right? So if the T1 is 30 degrees along the y-axis and T2 is the same, so the T1 and the T2 both are at 60 degrees in respect of the x-axis, and then also it will be the same. So T1 is equals T2. So basically if we just type and figure out T1 cosine of 60. Why cosine of 60? Because this angle right here is 60, this angle right here is 60, so we can type T2 cosine of 60 as equals oh sorry, they are equal, sorry, they are in the opposite direction, so they are equal. Okay, so if the cosine 60 are being cancelled out, so T1 is equals T2, we can tell that easily. So T1 is equals T2. Then if we take out the component at y-axis of T1 and T2 both, so T1 sine, they are 30 degrees along the y-axis both, so T1 sine 30 plus T2 sine of 30 equals both of the components working at the y-axis are equal to the force working at y-axis but in the opposite direction, which is 600 Newton, so equals 600. And now if we calculate, if we just calculate, so it is T1 sine 30, T2 sine 30, 2 T1 sine 30, sine 30 equals, okay, I think I've done something very state. Let me just oh no, sorry, it's not sine 30, is sine 60 actually. So this is this right here, the angle is 60. This right here the angle is 60, and this right here the angle is 60 as well. So 60 and 60, t1 sine 60, it will be t1 sine 60, so it will be mean. So calculating, so let t1 sine 60 plus, we got our relation t1 equals t2, so t1 sine 60 equals 600, so we can easily say 2t1 sine of 60 equals 600. So calculating for t1, if we calculate 2 multiply sine of 60, root 3, 600 by root 3 is 346.41, 346. That's our one answer. So it's also equals to 2. Then if we draw a free body diagram for the second one, the first one is done, the first step is done. So if we draw a free body diagram for the second one, so let us think about copy paste. Okay, so for the second one, the free body diagram, for the T4, T1 and T3, and the rope which is clamped with the ceiling, if that is the case, this, okay, yeah, so this right here is T4, this right here is T1, this right here is T3, right? So the horizontal component of T1 is working at the same direction of T3, of the direction, like the horizontal component of the first tension is working at the same direction where the component or the tension itself of the third tension is working. So both, like if we can write that T1 cosine of 60 plus, because the angle between here is 60, so we have to write 60, and plus T3 is working at the same direction. The T1, the first tension's horizontal component is working at the same axis as the T3 is working at the same axis as well. So T1 cosine 60 plus T3 equals the working component of T4 at horizontal. So T4 cosine, now this angle right here is 20 degrees. How we were managed to figure that out? Actually, this is 70 degrees, right? This is 70 degrees with no doubt, right? Now if we have to this. This is 20 degrees. If this is 70 degrees, this total angle is 90 degrees. This is 20 degrees. So this is if the component, the horizontal component, if we take of T4 is, it should be T4 cosine 20, right? T4 cosine 20 or T4 sine 70, whatever you can write. You can just, you have to just balance out the logic. You can write whatever you want, but you have to balance out the logic. So T1 cosine 60 plus T3 equals T4 cosine 20, right? T4 cosine 20, T1 cosine 60, T3. Okay, then so we know the value of T1. The value of T1, if we write the value of T1 is 346.41 cosine of 60 plus T3 plus T3, we don't know the tension, and is T4 cosine of 20. We still don't know the value of T3 and T4, right? We still don't know the value of T3 and T4. How we will be managed to bring out T4? We can't bring out T3, we can't manage it out because there's no clue to do that, but we have a clue to figure out what the T4 will be. So if we just focus right over here, the y-axis, on the y-axis, if we take the component of T4 at the y-axis, so it will be T4 sine of 20, and if we take out the component of T1 at the vertical axis, so it will be T1 sine of 60, right? So T4, so can write that T4 sine of 20 equals T1 sine of 60. From here we know T4 sine of 60 is equals 346.41 sine of 60. Then we can get our T4 or desired T4 from here. If we calculate 346.41 multiply sine 60, okay, I think here it should be 20. Okay, so sine 60 by sine 20, so it's 877.14 Newton. So if our T4 is 877.14 Newton, so now we will be able to know that what will our T3 be. So if we just input the value of 77.14, then we will be able to calculate the T3 from here. So T3 will be 877.14 cosine 20 minus 346.41 cosine 60. So 651.04 651.04 Newton. 651.04 Newton. We got our T3 as well. So now T1, T2, T3 and T4 are figured out. So the first free body diagram is complete. The task of second free body diagram is also complete. We have to complete the last one. So the free body diagram we have to draw along T3, T5 and T2 tensions. So for the third free body diagram, to take out, let's say this. To take the free body diagram at here, T4, it's T2, it's T3, it is T3 and it is T5. Now we know that what is the value of, so actually we can tell that by common sense that T4 will be equal to T5. Why? So why it will be T4 will be equal to T5? See here, the first tension and the second tension are both along 30 degrees to the perpendicular. So both are supplying equal tension forces. So forces to their connecting ropes. For T4 it is same, for T5 it's also same, for T3 both are common. The T3 is common between both of the tensions. So if the T4 is equals something, so T5 is also equals that magnitude. So T4 is equal to T5. We can prove that actually. T5, if we take out the component at the horizontal, so it will be T5 cosine 30, T5 cosine 20, T5 cosine 20 and it will be equal to T3 and the horizontal component of T2, so it will be T2 cosine 60. We know T5 cosine is equals, we know the T3 which is 651.04, 651.04 plus the T2. For the T2 it's 346.41, 346 of 6t. So if we to calculate this T5 here, so 651.04 plus 346.41 sine 60 by cosine of 20. I think there's some okay. This should fine. Okay. Let's cosine. Okay, so 877, yes. So it's equals 877.14 as well. So we can tell it automatically that T5 will be equated to T4, but for the sake of the proof we had to do that, and we can also do that by the help of perpendicular axis and y axis. We can prove it via the functions using sine functions as well. So taking out the components at perpendicular, we can also prove that, but we can also prove that using horizontal components, right? So that was it. We got all our magnitude of tensions. This was the problem. At this problem, there's a figure which describes that an object is hanged with the support of two ropes. One is clamped with a wall and one is following a sequence of another ropes tied up respectively with the wall and the ceiling, and this whole system, whatever we can say, the whole mechanics or the mechanism is just trying to balance and trying to hang the ball or the object. The question asked us to find the four tensions working in the following figure. So let us start by just drawing free body diagrams. Free body diagrams help us a lot in solving these kind of problems, and any kind of problems free body diagram is obviously it's needed. So if we just it's y-axis and assume this is x-axis, right? So if this is x-axis and this is y-axis, now at step 1 you have to think about this t1, t2 and this objective. Okay, I forgot to mention the weight of that objective. Okay, the question, the weight of the object is 80 Newton. Okay, the weight of the object is 80 Newton. 80 Newton. Weight of that object is 80 Newton. Okay, if we can just write it, weight 80 Newton. So yeah, weight 80 Newton, right? So the weight is working downwards, okay, due to the gravitational force, and the tensions are divided not equally because of the angles. Along y-axis, the angle along T2 is 25 degrees, and for this is clearly a 90-degree angle along y-axis, right? If we try to solve it, we can derive two equations from here actually. For T1, if we separate it in two components and take out the T1 sine component, right, the component at y-axis perpendicular, T1 sine of T1 sine of 0 or cosine of 90, whatever you can say, right, because it's on the 0 line, so it's 0 clearly, plus T2 Now this is cosine 25. If we take out, if we assume this is okay, if we assume this is y-axis, so we have to take sine, but we can also take cosine if we want cosine 25 or sine 65, whatever we want. At our ease, we have to do it and solve it. So it's cosine 25 or sine 65, like 90 minus 25 is 65, so sine 65, sine of 65, right, equals 80 Newton. The force working downwards, the force working downwards. This is an equation. Now this is equation number 1. Now if we can take the component at x-axis of both tensions, so T1 cosine of 0, because it's the component that the T1 itself is working at the x-axis, and for the T2 it's cosine 65, or otherwise we can say that it is T2 sine of 25. Okay, T1 cosine 0, T2 cosine of 65. Oh, both are equals, so we can't write it down, plus we can have to write it equal or minus equal 0. So it is another equation right over here. So okay, if we continue this, actually we have to take out, if we have to figure out any one of the tensions. So if we figure out T1, so it's basically the cosine 0 is equals 1, so T1 is basically T2 cosine of 65. This is another equation. Okay. Now if we put T1, if we put equation 2 to equation 1 into equation 1, so T2 of cosine 65 multiply sine 0 plus okay, actually I've done something fundamentally wrong, I think. No, we should continue, so because sine 0 is 0. Okay, so we can write at 0. T2, okay, we can figure out T2. Okay, 80 by sine 65, so 88, T2 is 88.27 Newton, and then we can put it right here, so 88.27, so it's equals T1 is equals 88.7 multiplies cosine 65, 37.3 Newton. We got T1 and T2. Now we have to figure out that for the T3 and the T4. It's easy. So for the T3 and the T4, you can just have a free body diagram. So we separated this. This is T3. This is T3. This is T4. And this is T2. this right here is 55 degrees angle. It is it is tilted 55 degrees angle along y axis. Okay, so we just we have the T2 right here. We have the T2, so we can divide it into components. Okay, it will help us. T4. About T4, we can actually figure out T4 easily, very easily, by dividing it into the perpendicular components, the components along y-axis. Also dividing the components along y-axis. So T2 sine of if we say that this is okay, for if this is 25 degrees, this is 90, 90, 25, so this should be 65, sine 65, right? This is 25. If we expand or continue the line, then here it will derive it, the here a 90-degree angle will derive, and here automatically it will speak it up for the value 65 degrees. So it is T2 of T2 of cosine 65, actually not sine 65, actually cosine 65, cosine 65. This angle right here, this angle right here is 65, cosine 65. So we need sine 65 actually at the y-axis, sine 65. So this, okay. Now we need the T4, the T4 at y. So the component of T4 at y is T4 sine of or we can say cosine of 55 or sine of, okay, cosine of 55, right? Cosine of 55, both are equals. So we know what is the value of T2. So 88.7 multiplied sine 65 equals T4 cosine of 55. So from there we can say, we can derive the T4. So what will be the T4? 88.27 multiplied sine 65 by cosine of 55 is 139.48, 139.48 Newton. So this is another one, 135.48 Newton. And we got our T4, we got T1, the T2, the rest is T3. You have to figure it out, it's easy. So about T3, it's working along x-axis. We have to take the component of T2 along x-axis as well as the component of T4 along x-axis, T3, and the T3 is working at the same direction. That will be working with the T2 at x. So T2 cosine of 65 equals T4 at x is cosine of or sine of 55. Okay, we know T3 plus we know the value of T2 is 88.27 cosine of 65 equals, we know the value of T4 is 139.48 sine of 55. So from there we can easily figure out the value of T3. So 139.48 sine 55 is 88.7. 76.95. So we got our T3 as well.